Hello everyone. Sorry for that little lag there. I thought I'd give this a try just to give you all a chance to maybe take part in something called video annotation. So we'll see how many of you figure out how to do it. I'll keep this short, but I'm going to go through some of the numbers that we were trying to put in your head, and I'm going to do the finger dance here with you, and we'll see how this works. As we went from section to section this week, we met each other, we got stuff going, and we were working on some base science knowledge. And some of that base science knowledge is predicated on some knowledge of math, particularly the circle. So we learned somehow that the circumference of a circle divided by its diameter is pi. And I'll have to figure out how to do a pi symbol here. The circumference of a circle divided by the diameter is pi. It's a ratio. It's 3.1417 yada yada yada, but it's a ratio. Since circumference has units of meters or feet and diameter have units of meters or feet, it is a unitless number. All true ratios are unitless. We learned, I hope, or started to learn, that the meter is the basis of the entire metric system, and it was an arbitrary unit thought up by the French when they strung a line from the North Pole. This is, of course, they didn't really string a line. From the North Pole through Paris to the equator, and they called that 10 million. From that we get the approximate circumference of the world going around the poles through Paris is 40 million meters. It turns out to be something like 40,008,000 meters, which is an additional 8 kilometers, but that was the basis. Now the meter is based on something different, but that was the original declaration, if you would, or the standard. And there's a lot of great history about navigating the world, and that you can find out in many different shows regarding Galileo and all these other figures over history. So we know that around the world, around the poles, is 40 million meters. From there you can go pretty far. If you look at the mass of the world, it turns out that the world as a whole turns out to be about 6 times as dense as water. So let's go and remember what we started to learn about water. Water, in fact, has a density of 1 gram per cubic centimeter, which is the same as 1 gram per milliliter. A milliliter and a cubic centimeter are units of volume, and they are the same. The word milliliter means 1,000th of a liter. Therefore, if you have 1,000 milliliters, you then have 1,000 grams, and you have a kilogram. And you get to the second, basically same definition of the density of water at 4 degrees Celsius, 39.6 degrees Fahrenheit, and that is 1 kilogram per liter. Of course, when we get to the true standards, we stay in our base units of meter, kilogram, which is an odd one, I must admit, and second, that we know that the density of water, if you want to keep it in true SI units, is 1,000 kilograms per cubic meter. And those are numbers that should go in your head, in your calculator, but probably better in a story that helps you to recount them. We learned that there are 7 standard units, basically, in the System International, and the rest start to be derived. They are distance, which is meters, mass, which is kilograms, time, which is seconds, the one I forgot, temperature, which is degrees Kelvin, with 1 degree Kelvin being the same as 1 degree Celsius in terms of shift, but the Kelvin scale being off something in the order of 273.15 or thereabouts to the centigrade or Celsius scale. We have current, which is an ampere. We have luminosity, which is measured in candelas. And finally, we have the concept of a mole. And a mole is a fixed number of molecules. And that one jumps around a little bit, but it's known typically as Avogadro's number. It is 6.02 times 10 to the 23rd. It is a number. So those are your standards: distance, mass, time, temperature, luminosity, current, and finally number of moles. These are some of the base things we know. We learned a little bit about the composition of the atmosphere and a little bit about the composition of the Earth per se, the whole Earth, not just the surface of the Earth, the crust of the Earth, the lithosphere, if you would. We learned that air is comprised of about 78% nitrogen, that has a chemical formula N2, 21% oxygen, that has a chemical formula O2, and 1% argon, which is a single atom, part of the Nobel gases. We learned, I think, that the concentration of carbon dioxide in the atmosphere is definitely going up, and it's somewhere in the order, and I'm probably going to get this wrong, of around 375 or 380 as measured at this station up in Hawaii, where they've kind of more or less is calling one of the stanzas when we measured CO2. If I didn't mention it, going back in time trying to figure out what was the CO2 much further back is often done by taking ice cores through Antarctica and sampling the little bubbles that are in the ice. So there's a lot of base science, and it does expand, but science coverage in the news and the like is much easier if you begin to understand some of these units. And you will also be pulling many things out of the literature. And so it's great to deal with water, because later on you're going to learn some base numbers for water as well. And we talked a little bit about, and we got all the points, for how many pounds are in a hundredweight. There's 100 pounds in a hundredweight. We talk about milking. And if we stick with our culture in Wisconsin, at least my daughter's culture and many of your culture, my culture is a little distorted, I have to say. I'm from Chicago and married to someone from LA. But we have to remember that a gallon is 8.33 pounds. Someone will say 8.34. But that, of course, is not our standard units of measure in the imperial system. Our standard units of measure are feet. And we'll call it pounds, though really it's slugs. So when we talk about weighing, 1 cubic foot of water weighs approximately 62.4 pounds. And here you then have the conundrum that pounds are units of force, and we quite often might say pounds force, and kilograms are units of mass. We might have remembered to discuss the definition of mass as being the amount of stuff or the amount of matter, something that occupies space. It is also mass measures the amount of stuff would be one definition, or eventually when we get into analogies, something's resistance to changes in inertia. That would be its measure of its mass. We did more. We did some experimentation in the lab, and we came up with basically around 21% of a moisture content when we completely saturated some basically gravelly soil, which was a mix of pieces of gravel. Now, I put this out, and I spoke not super slow, but you can write some of these things down, and what I'm going to ask is some of you to try to use the annotation tools that you'll see. There's a little thing floating around here that you should be able to click on and try to annotate this video. Now, my mouth might not match what I said, And that's when that occurs, your best bet is to just stop looking at my mouth and listening to what I said. So that's what we covered the first week. For those of you who have done readings in chapters 1, 2, and 3, and start to look, we looked up at the scars and we learned about a guy named Neil deGrasse. And so I would truly suggest that you go out and look at him, or Jack, I think it's Herkheimer. The video will be kind of attached to this one. And begin to enjoy, as we head into the fall, towards the autumnal equinox, the world around you outside. You start looking up and down and then into your calculator, computer, or whatever, and starting connecting some of these numbers and concepts to the world around you, so you carry it with you and pass it on within engineering and within life. Thanks for listening. Have a great weekend.